And there's many dimensions of this. One is simply, is the airflow large enough to the filter? But another one is the system that brings air through that filter actually operating? And the figure shows a common scenario. This is data from about 7,000 homes with forced air heating and cooling systems in North America. And each dot here represents a month of operation, where the y-axis is the runtime, how often the system operates, and the x-axis is the outdoor temperature. And so there's a couple of big picture messages from this figure. Number one is, there's a little bit of structure, but not a ton. Mostly there's a lot of variation. So in some homes, the system runs a lot. In other homes, it runs much less. And there's a little bit of dependence on the climate. There's that kind of U shape to it. So as it gets colder or hotter, a system is more likely to run. But the overall message that I think is really important here is that red dashed line. That shows the median runtime, or the median fraction of time that the system operates in these homes. And it's about 18%. So what that means is that if you have a filter in one of these systems, 80% of the time, or a little bit more than that, air isn't even going to go through the filter. So it doesn't matter what type of filter you have most of the time. And this is because in most of our residential systems, we couple airflow and conditioning. So when the thermostat calls for heat or cooling, the system operates. And when it's not calling for heat or cooling, the system doesn't operate. And that's true in residential buildings as well as some other types of buildings as well. And so there's really this issue of, you can't simply just have a good filter. You have to make sure that air goes through it. Now let's talk about filters themselves. I think a common conception is that the smaller a particle is, the harder it is to filter. And that's not true. Most filters have what's usually called a U-shaped curve, like the one shown in the picture here. And you can see that particles in the range of about 0.1 to about 0.3 microns in diameter are the hardest to remove or have the lowest efficiency. And bigger particles are more likely to be removed because of inertial mechanisms. And smaller particles are more likely to be removed by something called Brownian diffusion. And this U-shaped curve shows up over and over and over again. And so when we think about this in the context of filtration standards and so on, you might have heard that a common recommendation for COVID-19 protection is a MERV 13 filter. MERV is a data product from a standard, an ASHRAE standard 52.2. And a MERV 13 filter has the efficiencies that I just highlighted on this graph. And so in particular, a lot of the transmission occurs in particles that are 1 to 3 microns in diameter. And you can see that the efficiency is 85% for those particles. And so this whole idea of filter efficiency is very important, because you have to make sure that your filter has sufficient removal of the size of particles that you care about. And then there's another layer of complexity. So one of the things that I do in my research is go out and look at the actual installed efficiency of different filters in different buildings. So this is a study we did in 20 Toronto homes. This is a MERV 14 filter, so quite an efficient filter. And you can see the efficiency is a function of particle size, like in the other graphs. And it's a little bit hard to see, but there's a black solid line there. That shows that the efficiency that you would expect from that MERV table that I just showed you, that was the test of the filter in an actual test lab. And what you see in all the symbols are, each symbol is associated with a different home. And you can see that in general, not for all homes, but in general, the efficiency was lower as the filter was installed. And sometimes it's a lot lower, especially for some particle sizes. And so you really run into this issue where it's insufficient to pick a good filter. You have to make sure that you're getting that efficiency installed in the system. And one of the main reasons for efficiency degradation is something called filter bypass. So this is a picture of a filter rack in a commercial building. And you can see that the filters are kind of pulling out of the rack, and they have both the very large gaps where they're pulling out of the rack and the smaller gaps around the filter and how it fits into the rack. And so what happens is that particles will preferentially go through those gaps that aren't filtered rather than through the filter itself. And so that's one reason why in situ efficiency is often lower than you would expect based on the rating. And this points to the importance of actually installing filters well if we're trying to use them to protect people in the building. There's other layers of complexity here too. Filters change in performance as they age. So this is some research that was done close to 20 years ago in a Finnish commercial building. And this is a very good filter when it's new. Those are the gray squares at the top. And then over time, the filter efficiency declined. And it declines because part of the way the filter removes particles is it's got what's called charged media or electret media in the filter. And that enhances removal, but over time that effect diminishes. And so you can see that at the end, this filter was rated for a year of life, but after 9 months, that's the triangles at the bottom, the white triangles, you can see it's declined in performance quite substantially, particularly for smaller particles. And so that's the reality that we live with, is that you have to make sure you're maintaining efficiency. And this is the same sort of data shown for residential buildings. You can see that the 3 filters that have an E at the end of their name, those are Electret filters. On average, they show declines at the end of their life, which was 3 months in this case, compared to when they were new. And so there is this real issue relating to filter performance declines, as well as filter installation issues in real buildings. And one last point I want to make about filtration. This is the result of a review where we found 16 articles in the literature that measured something called effectiveness, which the higher the effectiveness, the better the filter is performing. And here you can see what those studies report for effectiveness versus the filter efficiency, or the MERV. And you can see that it's kind of all over the map. There's a little bit of structure, but not a ton. So in some cases, high MERV filters are performing well. In other cases, high MERV filters are performing poorly. And so there is this real question of context. Just because you have a good filter, it isn't necessarily going to perform well. And for the record, a lot of the reasons why these filters aren't performing well in these homes have to do with potentially some of the installation issues like bypass, as well as issues like overall ventilation rate. In a very well ventilated environment, the filter doesn't contribute as much to removal. And so if I were to summarize everything on filters, I would say, install a good filter, use it well, make sure that lots of air goes through it, change it frequently and potentially carefully, because there might be active microbiological material on it. And certainly it's not a silver bullet. Don't rely on it as the only approach. So if we move from filtration to ventilation, the article that I think informs most of my thinking about ventilation and its potential to help us with COVID-19 is this article from a little over a decade ago by Hugo Lee and his colleagues, where they looked at about 40 articles or so in the literature that looked at the association between ventilation rate and transmission of infectious diseases. And there was many diseases that were included here, obviously not COVID-19, because this was before COVID-19, but SARS-1 is included in this review. And there are 2 main points of this article that I've summarized in the quoted text. The first is that there is sufficient evidence to demonstrate the association between ventilation and disease transmission for a variety of diseases. However,